Welcome to X-ray diffraction virtual training. We're starting this training with some background information on X-ray diffraction. Later videos are going to focus more on swapping out components on the instrument and also how to use the software. I encourage you during all of these trainings to take notes and especially to write down the questions that you have as you're going through these trainings. We will have a live training, possibly not in person, but still live, where you can ask me those questions, and I hope to have good answers for you at that time. So to begin our discussion, we need to talk about Bragg's law. Bragg's law was developed by Lawrence Bragg and his father, William Henry Bragg, and it really defines the X-ray diffraction condition. So let's talk about the terms in this equation. N is just an integer, 1, 2, 3. Lambda is the wavelength of X-rays that you're using in the experiment, so that's going to be a constant value. D is the atomic spacing, and in this diagram on the right, it's essentially the spacing between two planes of atoms. And finally, theta is going to be your angle of diffraction. You'll see that illustrated in this schematic as we go through this. So let's talk about how we would derive this equation. And what I'm showing here are X-rays with a certain wavelength lambda that are irradiating our sample. And in particular, I'm showing two individual waves. The top wave diffracts off the top plane of atoms, and this second wave diffracts off the second plane of atoms. Now, there is a slight difference in the distance that the second wave has to travel as compared to this first wave. And we can see that illustrated here. So in this case, this second wave has to travel the additional distance indicated by these blue lines and still make it out of the sample. Now, there is a particular condition under which the length of these blue lines is going to equal, for example, 1 wavelength of that X-ray beam that's coming in. And when that happens, we meet the Bragg criteria. And so essentially, in this experiment, we are going to be changing the angle of incidence. We're going to be changing theta. And theta is going to change both on the source side and the detector side. And so as theta changes, we will come upon conditions under which the length of this additional blue line, the length that the second wave has to travel, is going to equal an integer number of wavelengths. And so another way to say this is to look at the geometry that's in place here. This single blue line, if we were just to use trigonometry, the length of that line is going to be equal to d sine theta, just as indicated on the right-hand side of this equation. Now, of course, the second wave has traveled twice that distance, and so we added 2 into the equation. And we say that when that distance is equal to an integer number of wavelengths, then we've met the Bragg condition. And when that happens, we have what we call in phase, that these waves are in phase. And that's what gives us signal in X-ray diffraction. So let's take a quick look at what in phase really means. If we were to look at two waves that were out of phase first, those waves would show something like you see here, where the peak of one wave would be directly over the valley of a second wave. And what we get in this case is destructive interference. Those waves essentially cancel each other out, and we get no signal. Now, if those waves line up perfectly so that they're both exactly on top of one another, we get what's called constructive interference, or these waves are said to be in phase. When that happens, you can see that the amplitude of this wave is now twice as high as it was originally. That gives us additional signal at the detector. Of course, we can be at some intermediate phase as well. In this case, I'm showing an example at 100 degrees, and we get something in between. But the key take-home message is that when we have constructive interference and our waves are in phase, then we are going to see X-ray diffraction. Now, you may have seen an example of a diffraction experiment at an outreach event. So one common outreach activity is to take a laser, shine it at a material that has a pattern, like a grating or something along those lines. And what happens is that even though you're shining one light in here, it diffracts off of all the patterns in here and gives us multiple spots, usually in a very nice grid pattern or some other very organized array. With the X-ray diffraction experiment, we're doing something similar. We are typically not doing a transmission experiment. As you see on the left, we're doing a reflection experiment. So the X-ray source hits our sample, and we get these diffraction spots on the detector. So let's take a little closer look at what we would expect to see over here for our X-ray diffraction experiment. Now, if you can create single crystals that you can see with the naked eye, then you should take them over to the X-ray diffraction facility in chemistry. They can produce very nice, beautiful patterns and solve those crystal structures for you. And so this is an example of the type of data you would get from those samples. So in this case, we have a crystal that is relatively large. I've said its volume is 10 to the 6th microns cubed. And in that case, we get a set of spots, diffraction spots, that correspond to the different spacings within that sample. But what if you can't grow a sample that's that large? Or maybe you have a thin film that has some crystallites in it. Well, let's pretend for a minute that you have just one small crystallite. In this case, the volume is only 1 micron cubed. You would see a similar pattern, but the intensity would be much weaker because we have less sample to diffract from. If we were to add one more crystal, indicated by the one here in red, you're going to get a new set of spots. They're going to be offset from the original spots because the orientation of the second crystal is different than the orientation of the first crystal. And if we were to add another crystal, again, another set of spots appears, and we can keep repeating this, adding more and more crystals. And you can start to see that a pattern is emerging as we go through this. The spots are starting to form essentially rings. And what we do in an X-ray diffraction experiment is we assume that your sample looks something like this on the left, where we've got all different orientations, all different possible orientations are represented in your sample. And so instead of seeing individual discrete spots, you see these rings because that spacing can be seen in all different orientations. So in the powder experiment that we're doing, what we typically do is integrate the intensity for each one of these rings, moving from an angle of 0 out to a higher angle of, in this case, 70 degrees. And we plot that intensity as a function of angle. So this is what your X-ray diffraction data will typically look like. But I wanted to walk you through how we actually get that data. Now, it is somewhat important to think about your sample and the orientation of the crystallites in your sample. Most of the time in powder X-ray diffraction, we assume that you have a sample that looks something like what you see on the left. Many crystallites, millions of crystallites, and they are present in every possible orientation. When you think about your sample, it might not be quite this ideal. It might have some preferred orientation, and I will make some comments about that later on in this training.